The objective of this lecture is to provide the introductory concepts that are used in dynamics. This lecture will be divided into the following parts. First, we will provide an overview of the subject of dynamics. Then we will provide the mathematical framework that is used for dynamics, and in particular, we will start studying the basic constructs of vector algebra. Now, within vector algebra, there are several key concepts that will be studied in more detail, and those include the concepts of scalars and vectors, and then key operations on vectors, and then the concepts of bases and coordinate systems, and then finally, the last part of this lecture will focus on coordinate transformations. So in order to get started, let's describe qualitatively the subject of dynamics. So dynamics is actually a subset of the subject of mechanics. The mechanics is the study of the response of physical systems due to actions applied to the system. Now, mechanics itself doesn't have anything to do with motion. The system could be moving, but it may not be moving. It's more generally, how does a physical system respond when an action is applied to the system? But within the subject of mechanics is the subject of dynamics. Now, dynamics is more specifically the study of the motion of physical systems due to actions applied to the system. So when we say a system is moving, what we mean is that the system's moving or doing something because there's an action being applied to the system that's causing it to move. Now, within the subject of dynamics, in order to study dynamics, we actually have to study two separate aspects and then put them together. Now, these two aspects are subjects in and of themselves. The first one is what's called kinematics. And the second is kinetics. Now, in kinematics is the study of the motion of systems without regard to the cause of the motion. Now, what we mean by that, when I say without regard to the cause of the motion, kinematics is the study of what's happening, but not the reason why it's happening. And that's really important. So it deals with things like position, velocity, acceleration, angular velocity, angular acceleration. But it doesn't deal with why the motion is occurring. It's more a concept of what is actually happening and studying what's happening. Now, kinetics is where the why the motion is occurring actually takes place. So kinetics is the study of the motion of systems due to actions applied to the system. Now, it may seem that that's the same definition as the definition of dynamics, but it is and it isn't. It's the same in the sense that in the study of kinetics, or the subject of kinetics, we're interested in those actions that are being applied to the system and how that actually causes motion. But before we can actually study what the motion is, we need to actually geometrically know what that motion would be due to the geometry of the system. So really, kinematics itself deals with geometry of motion. So kinematics deals with geometry of motion. Whereas kinetics deals with or focuses on with actions applied to the system. Now, these two subjects actually come together at this point right here, where the interface between these two, in order to bridge the gap between kinematics and kinetics, we actually have what is classically known as the laws of motion. What we mean by that is that somehow we have to connect the physics, which are the actions that are applied to the system, to what is happening and how those actions actually cause this motion. And that's where the laws of motion come into play. Now, in the study of dynamics, at the outset, these laws of motion are either, if you're dealing with translational motion, they're Newton's laws. If you're dealing with rigid body motion, which is what happens when you have a rotational motion, then those are Euler's laws. Now, what's really important in all of this is that there's one thing that needs to be described mathematically in completeness, and before we can actually even get to the subject of kinematics, and that is vector algebra, because all of mechanics is based on vectors. So in order to be able to describe the subject of dynamics quantitatively, we need a mathematical background, and that mathematical background is what's called vector algebra. So the first part of this lecture is going to focus on the basic mathematical concepts of vector algebra. So vector algebra provides the mathematical background for studying dynamics. So if you're studying all of mechanics, but in particular studying dynamics, this is the mathematical background required to study the subject of dynamics. Now, vector algebra is, as stated at the beginning, divided into many parts, but the key parts of of vector algebra that we're going to study in this lecture are going to be as follows. First, we're going to define scalars and vectors, which was stated before. And then we are going to describe the key operations on vectors. And then we are going to describe this very important construct of what are called bases and coordinate systems. And then finally, we're going to study coordinate transformations. Now, what's important about all of this math is that once we have put this math in place and we have all of these key constructs available to us, we can then use these key ideas mathematically to be able to describe kinematics and kinetics. So kinematics and kinetics can then be described. So we're not going to do kinematics and kinetics in this particular lecture, but we're going to do these four major parts of vector algebra. So the next step is going to be to start with scalars and vectors and move our way through all of these key concepts. So we start with scalars. A scalar is any quantity that can be expressed as a single real number. A set of real numbers will be denoted by the symbol R. So therefore, if B is a scalar, then B is said to be an element of the real numbers. Now, next we have to define vectors, but before we actually define vectors, we have to define what's called Euclidean space, which in this case is actually three-dimensional Euclidean space. So three-dimensional Euclidean space which is denoted E3, is the space in which geometric points lie. Now, a point is a zero-dimensional object in E3. Now, using points and the construct of this space in which these geometric points lie, we can actually define vectors. So suppose now that we have 2 points. I'm going to call those points O and P. So let O and P be points in E3. Then the line that connects O and P can be thought of as a vector. So the way this works is as follows: is I have a point O, I have another point P, and if I take the line, the directed line from O to P, that creates a vector. I can arbitrarily just call this vector B. Now, it can be seen that there's a distance between O and P, and there's a direction from O to P. So the magnitude of a vector is the distance between the points O and P. Now, that's in this context here, but it's true in general anyway, which is that magnitude of the vector is the distance between these points. And the direction of B, or of the vector, is the vector itself divided by its magnitude. So again, if I consider the vector to be B, so I'm considering B to be my vector, then what I can do is I can define the distance between or the magnitude of the vector, and then I can define the direction of the vector. So let's do that. That we're going to define equal this symbol, which has double vertical bars around B, is going to be defined as the magnitude of B. And then the direction of B, which I'm going to call u sub B, is going to be equal to the vector divided by its magnitude. Now you can actually see that if I take the magnitude of UB, that's equal to the magnitude of B divided by magnitude of B, which is just equal to the magnitude of B divided by the magnitude of B, which is just equal to 1. So that implies that UB is a unit vector. Now we need this construct of a unit vector because without it we can't do other algebra that we're going to need to do later on. So a unit vector is one whose magnitude is unity. And I can say that is 1, meaning the magnitude is 1. Now, once I do this, if you just look at this equation that I have up above, which for UB, you can actually just rewrite this, and you can see that B is equal to the magnitude of B times UB. So the first part here is the magnitude, and the second part is the direction. So if I just sort of break this up into two parts here. Here is the magnitude, and here is the direction. So what that tells me is that every vector has both magnitude and direction. So therefore, every vector has magnitude and direction. Also, and this is important, just like points, vectors lie in E3. Remember that a point was a zero-dimensional object in E3. A vector is a one-dimensional object in E3. Now that we've defined vectors, we can actually start defining operations on vectors. And these are like key operations that apply to all vectors. So we're going to start talking about key operations on vectors. The first of these operations is going to be what's called the scalar product. So, scalar product. It's also called the dot product because of the symbol that's used to define it. So what we're going to do is we're going to say let A and B be vectors. Then the scalar product between A and B is defined as follows. We say A and then we use the symbol dot in between. And that's defined as the magnitude of A times the magnitude of B times the cosine of the angle between the two vectors. And I'm going to define that angle as theta. So theta is the angle between A and B. Schematically, what that looks like is as follows. If I have a vector, call this vector A, and I have another vector, I'll call it B, theta is the angle between A and B. Now, you can actually see from this definition that there's a way to be able to define the magnitude of the vector. So suppose now that the scalar product of a vector B with itself is taken. What does that mean? Well, that means that we're taking B dotted with B, taking the scalar product of B with itself. That is going to equal, from the definition of the scalar product, the magnitude of B times the magnitude of B times the cosine of the angle between B and B. But there is no angle between a vector and itself, so the cosine is going to be taken on the angle 0 because the angle between a vector and itself is 0. Now we know that the cosine of 0 is equal to 1, which directly implies that B dotted with B is equal to the magnitude of B squared, which further implies that the magnitude of B is equal to the square root of B dotted with B. So that's how we actually compute the magnitude, which is we take the dot product of a vector with itself and we take the square root of the result, and that's the magnitude. Now, once we have the definition of the magnitude and we have the scalar product, we can actually define this concept of what's called orthogonality between vectors. So we're going to call this orthogonality between vectors. So again, we're going to do this from the start. We're going to say let A and B be, now we're going to put a stipulation on this, which we're going to say be non-zero vectors. What that means is the magnitude of A is not equal to 0, and the magnitude of B is also not equal to 0. Now, if that's the case, we can say, so we say that A and B are orthogonal if the following condition is true. A dotted with B is equal to 0. So that's the definition of orthogonality. And remember that it's really important that this condition that neither A nor B have 0 magnitude be true. Because if either one of the vectors has 0 magnitude, this condition, it doesn't really have a whole lot of meaning because you're just taking the dot product of A with 0. Now, given that we've done that, we can use orthogonality of vectors to define the next key operation, which is what's called the vector product. And this is often called a cross product because, again, the operation that's used to define it. So we're going to say let A and B be vectors. Then the vector product between A and B is defined as follows. It's A, and then we use the operation cross. And that's equal to the magnitude of A times the magnitude of B times the sine of the angle between the two vectors times a vector that I'm going to call n. Now, n is the unit vector in the direction orthogonal to both A and B in a right-handed sense. And since that's a lot to write, we'll have to explain what all this means. So let's say where n is the unit vector orthogonal to both A and B in a right-handed sense. So let's describe what that looks like in a picture. So let's draw this picture. So this direction is, or this vector is A. This vector is B. And what I'm going to do is I'm going to imagine that I'm going to sort of superimpose on this the following things. First, I'm going to say that A, imagine that it points along the index finger of the right hand, and B points along the second finger of the right hand. Then A cross B, because it has to be in the direction n, there's A cross B, it has to point along the thumb of the right hand. And the unit vector in the direction A cross B is n, and that vector is orthogonal to both A and B in this right-handed sense. Now, the right-handed sense comes from the fact that if I curl my fingers from A to B, in other words, if I curl my index finger towards my second finger, then my thumb is pointed in the direction normal to both A and B in a right-handed sense. So these directions here, the index finger, second finger, and thumb are all with regard to the right hand, not with regard to the left hand. So the index finger second finger and thumb are those of the right hand. So that's why n is the unit vector orthogonal to a and b in a right-handed sense. Now, once we have this concept of right-handedness, because that's the convention that we use. So this is what's called the right-hand rule. The right-hand rule always corresponds to how the cross product or the vector product is defined. That's what we just developed. Now, using this right-handed convention, we can actually start developing what's called a basis for three-dimensional Euclidean space, and then use that to be able to start expressing vectors. So now we're going to talk about bases for three-dimensional Euclidean space. So suppose now that the set E1, E2, E3 is a set of three mutually orthogonal unit vectors such that E1 crossed with E2 is equal to E3. So what that means is that because these are all unit vectors, so we have that the magnitude of E1 has to equal the magnitude of E2 has to equal the magnitude of E3, which is equal to 1. But because it satisfies this condition that E1 crossed with E2 is equal to E3, it actually satisfies the right-hand rule. So this is what this set looks like. If I draw these three vectors, I have E1, I have E2, and I have E3. And these vectors are they're mutually orthogonal. So the angle between E1 and E2 is pi over 2. The angle between E2 and E3 is also pi over 2, and the angle between E1 and E3 is pi over 2. Now, what we get when we do this is we can now use this construct to be able to express vectors. So this quantity, E1, E2, E3, is what's called a right-handed orthonormal basis. So the set, and I'm going to call it E now, equals E1, E2, E3 is called a right-handed orthonormal basis for three-dimensional Euclidean space. Now, we normally don't use the full terminology right-handed orthonormal basis. So as a shorthand, E will be referred to as simply a basis. Instead, like I said, instead of saying right-handed orthonormal basis, we just say basis. Now, once we actually have a basis, we can define or we can describe or express vectors in that basis. So in terms of the basis E, the vector B can be expressed as, we can say B is equal to B1E E1 plus B2E E2 plus B3E E3. Now you'll notice that suppose I take the scalar products in the three directions E1, E2, E3. So let's just do that. So taking the scalar products in the directions E1, E2, and E3 gives the following. We've got B dotted with E1 is equal to B1E E1 plus B2E E2 plus B3E E3 dotted with E1. But because E1, E2, and E3 are orthogonal to one another, this just leaves me with B1E. And similarly, B dotted with E2 is equal to B1E E1 plus B2E E2 plus B3E E3 dotted with E2, which is equal to B2E, and then B dotted with E3 is equal to B1E E1 plus B2E E2 plus B3E E3 dotted with E3, which is equal to B3E. Now, these three quantities, B1E, B2E, and B3E, are defined as the components of the vector B in the basis E. So the quantities B1E, B2E, B3E are called the components of the vector B in the basis E. Now, what you can see from this is that let's suppose that I picked a different basis. So I'm going to call this basis U. And it's equal to U1, U2, U3, but it's not equal to E. Then, if B, or I could say it this way, expressing B in the basis U gives that B is equal to B1U U1 plus B2U U2 plus B3U U3. Now you'll note that even though this is actually, this last expression, this is actually the vector B, and so therefore it has to equal what I had before. It turns out that that even though the vector is the same, the components are not the same. So in other words, while B is the same vector as before, the components which in this case are B1U, B2U, and B3U, are not equal to the components B1E, B2E, and B3E. So we can actually abbreviate this a little bit nicely with shorthand, which is that we use this a lot, which is that when we use the expression B and then we say subscript E, we're going to call that a column matrix, which will be B1E, B2E, B3E. And this terminology means the vector B expressed in the basis E. And that actually gives us a nice way to be able to describe the expression of a vector in a particular basis. Now notice that these three numbers that have been arranged in a column, which are B1E, B2E, and B3E, those three together do not form a vector. The vector lies in three-dimensional Euclidean space, but these three values are just numbers. They are what are classically, or what would typically be called a column matrix. And that column matrix in this case is the representation of the vector in the basis E. So that's another way of being able to write this, which is that this is the representation of B in the basis E. Now, once we have this concept of expressing vectors in a particular basis, we can actually start using it to be able to do coordinate transformations. But before we do that, we need to define one other concept, which is that of a coordinate system. So that's the next thing we're going to define, is a coordinate system. So coordinate systems. So suppose that E, which is equal to E1, E2, E3, is a basis, and that O is a point. And furthermore, suppose that all distances are measured relative to point O. What does that mean? It means that if I'm calling something, or I'm saying something has a particular distance, that distance is being measured relative to this point O. Then what I can do is I can combine the point O with the basis. So the point O defines an origin, which, as stated, is a point from which all distances are measured. So I know that sounds a bit repetitive, but it's important to understand that that point is actually called an origin. So if I combine an origin with a basis, so an origin together with a basis is called a coordinate system. Now, it doesn't look much different from just a basis itself, but really what we've got is we've got a point O, which is a point from which all distances are measured. We have these basis vectors, which are schematically E1, E2, and E3. And if I have a point P out here, and I take the vector from O to P, then if I'm measuring distance, in other words, if I'm saying that P is a certain distance away, that distance away is being measured relative to O because O is the origin of the coordinate system, and the basis is E1, E2, E3. Now what we can do is we have all the information that we need in order to be able to define coordinate transformations, which is how to change the representation of a vector from one basis to another. So what we're going to do is we're going to define coordinate transformations through the concept of going from one basis to another basis. So coordinate transformations. Now, the way coordinate transformations start is as follows. Is we say let E equals E1, E2, E3, and U equals U1, U2, U3, be bases for three-dimensional Euclidean space. And because we're defining them as bases for three-dimensional Euclidean space, that means that we can express these vectors in terms of one another. So what I'm going to do is I'm going to start by expressing the vectors U1, U2, U3 in terms of the basis E1, E2, E3. So then the basis vectors U1, U2, and U3 can be expressed in the basis E as follows, which is we can say that U1 is equal to C11 E1 plus C12 E2 plus C13 E3, and we can say U2 is equal to C21 E1 plus C22 E2 plus C23 E3, and then U3 is equal to C31 E1 plus C32 E2 plus C33 E3. Now, I haven't done anything other than just say that each one of these vectors, U1, U2, U3, can be expressed in terms of the basis vectors of the other basis. Now, these quantities, Cij, so the quantities Cij for I and j going from 1 to 3 are called direction cosines. Now, there's a reason why they're called direction cosines. It's because, let's look at taking the dot product between any of the basis vectors that define the basis u and any of the basis vectors that define the basis e. If I take well, let's do it the other way. If I take ui dotted with ej, what do I get? Well, that's equal to the magnitude of ui times the magnitude of ej times the cosine of the angle between the two, which I'll call theta ij. But the magnitudes of these vectors are all 1 because they're all basis vectors. So that's just equal to cosine of theta ij. But if I look at the expressions that I have here, you can see that if I take ui and I dot it with ej, I just get the coefficient cij. So that's equal to cij. So because cij is a cosine of an angle, and it's a cosine between two directions, which in this case are ui and ej, it's called a direction cosine. That's where the term direction cosine comes from. So these coefficients are direction cosines. Now what we can do is we can use these expressions here that we have that relate the basis vectors u to the basis vectors in e to be able to come up with a coordinate transformation between the that takes components of the vector in one basis and transforms it to components of the vector in the other basis. And so the way we're going to do that is as follows. We're going to come up with expressions for b in terms of the different bases, and then we're going to set things equal to each other in these expressions in such a way that we can actually finally come up with the equations that define this coordinate transformation. So recall that b is equal to b1 e e1 plus b2 e2 plus b3 e3. But that's also equal to b1 u1 plus b2 u2 plus b3 u3. Now suppose that I make the substitution of u1, u2, u3 in terms of e1, e2, e3, which is what I had from the previous page. So then what I'm going to get when I do that is I'm going to get b1u, and now I'm going to substitute for u1. That's c11 e1 plus c12 e2 plus c13 e3 plus b2u times c21 e1 plus c22 e2 plus c23 e3, and then finally I have b3u times c31 e1 plus c32 e2 plus c33 e3. Now what I can do is I can combine all the e1 terms, e2 terms, and e3 terms. And if I do that, I can rearrange this last expression to look as follows, which is I get c11 b1u plus c21 b2u plus c31 b3u. This whole thing is multiplied by e1, and then we add to it c12 b1u plus c22 b2u plus c32 times b3u times e2, and then finally I've got c13 b1u plus c23 b2u plus c33 b3u times e3. Now let's look at this last expression and compare it to where I started. Notice that when I started, I wrote b in terms of e1, e2, e3, but the components were b1e, b2e, and b3e. Then I said that that has to equal the expression in terms of the basis vectors u1, u2, u3, and then I substituted for u1, u2, u3 to obtain a second expression in terms of the basis vectors e1, e2, e3. So the first expression I have on this page in terms of e1, e2, e3 has to equal the last expression that I have on this page. So you wind up with the following three equations. which is you wind up with B1E is equal to C11 B1U plus C21 B2U plus C31 B3U. And then the second equation is I have B2E is equal to C12 B1U plus C22 B2U plus C32 B3U. And then the last equation is B3E is equal to C13 B1U plus C23 B2U plus C33 B3U. Now you'll notice that because of the way I defined a vector expressed in a particular basis, I can actually use these three equations, and I can write it exactly the way that I had written it earlier, where I defined that construct of a vector being expressed in a particular basis. And when I'm done doing this, you'll see it, but we're going to go through the steps and see what this now looks like. So in matrix form, we have B1E, B2E, B3E is equal to C11, C21, C31, got C12, C22, and then C13, C23, C33 times B1U, B2U, B3U. Now, if you look at this expression, you'll actually see that on the left-hand side, this quantity on the left is actually equal to the vector B expressed in the basis E. On the right-hand side, all the way off to the right, I have that this column matrix is the vector B expressed in the basis U. So that means that the matrix that's sitting between these two, which is a 3 by 3 matrix, has to be a transformation from U to E. So in the end, what I wind up with is I wind up with this matrix CUE. This is actually a direction cosine matrix that defines the transformation of, so from the basis U to the basis E. In other words, this matrix transforms components of the vector B expressed in the basis U to components of the vector expressed in the basis E. So let's say that. So in other words, C U to E transforms components of the vector B in the basis U to components of the vector B in the basis E. Now, if you look, you can actually just see, if I put an equal sign here, that it says B subscript E is equal to CU to E times B subscript U. I could write that again just for completeness, but that gives us a way to be able to transform components of a vector. So we can do this in a relatively straightforward manner now, which is that we can more compactly B expressed in E is equal to the transformation from U to E times B expressed in U. Now, there's a converse, which is that we can do the exact opposite, and this is how you relate coordinate transformations, which is that suppose that I want to go the other way. So suppose I want B expressed in U, and I want that to equal the transformation from E to U times B expressed in E. Well, the only way that's going to happen, let's look and see what happens when we actually substitute this in to the expression above. So if I substitute this last expression into the first expression, what do I get? So substituting the second expression into the first expression gives the following. We get B expressed in E is equal to CU to E times B expressed in U. But B expressed in U is C E to U times B expressed in E. Now, given that the end result has to be the same as the beginning result, that means that these two operations have to be inverses of one another. C U to E times C E to U has to give me the identity matrix. Now, there's another property which I won't derive here, but it's worth noting, is that the determinant of a direction cosine matrix, any direction cosine matrix, is actually equal to 1. And this actually implies that a direction cosine matrix C is what's called an orthogonal matrix. Now, an orthogonal matrix has a property that is actually worth noting, which is any orthogonal matrix. So C is an orthogonal matrix, and the property is as follows, is that the inverse of an orthogonal matrix is actually equal to its transpose. So what that means is that the matrix CU to E, because it's the inverse of the matrix CE to U, they're actually transposes of one another. So this implies that C U to E inverse is actually equal to C U to E transpose, and that's equal to C E to U. So what we actually have here is a much simpler construct from just a general inverse. We actually have this transpose property with direction cosine matrices, and it makes it easy to go back and forth now. So if we want the transformation from E to U, we just take the transpose of the transformation matrix from U to E, and we get the inverse transformation. So we now have completed the description of coordinate transformations, because we have a way of being able to transform components of a vector from one basis to another, which takes us to the end of this particular lecture, and we can summarize now what we did in this lecture. So as a summary of this lecture, let's remind ourselves of what we did. So the first thing we did was we provided an overview of the subject of dynamics. And in particular, we described kinematics and kinetics as being the two key parts of dynamics, and then their connection briefly we described as being the laws of motion that connects kinematics to kinetics. Then we provided the mathematical background for dynamics, and in particular we provided the mathematical background of vector algebra. And that background included scalars and vectors. So we described scalars and vectors. We then provided the key operations on vectors. And in the process of doing that, we actually described the two key operations of a scalar product and a vector product. And after we described those key operations, then we described bases and coordinate systems. And finally, we described coordinate transformations. We can now use these concepts to be able to start the study of dynamics. And in particular, the first thing we're going to do is start the study of kinematics, and then we're going to go into the study of kinetics. And then we're going to connect the kinematics with the kinetics after we describe some basic concepts in kinetics with the laws of motion that allow us to describe quantitatively how systems and why systems actually move. And that will be in future lectures.